Hey everyone, I'm Michael, a curriculum manager here at Udacity. I'm also a machine learning and self-driving car enthusiast. Like yourself, I was originally a Udacity student. I actually learned Python through Udacity in the Intro to Computer Science course. After that, I took the machine learning nano degree and then the self-driving car engineer nano degree. My machine learning capstone was actually on deep learning for lane detection. Shortly after completing those programs, I joined Udacity. Since then, I've built some of my own edge applications using computer vision models on a robocar, which is sort of a small-scale self-driving car, and I've also deployed my lane detection model on mobile devices. In this next course, you're going to build some really great applications, and I'm excited to get started. As we start out this course, let's first look at what AI at the edge is. The edge means local or near local processing, as opposed to just happening anywhere in the world with the cloud. These type of applications are often used where low latency is necessary, or even when a network may not always be available. If there's a need for real-time decision making, an edge application is great to use. Many applications that use the cloud get data locally, send it to the cloud, process it, and then send it back. When using the edge, there's no need to send that data to the cloud. Your application can potentially be more secure and have less impact on the network. The edge does not mean no cloud usage whatsoever. Edge AI algorithms can still be trained in the cloud, but get deployed at the edge. Now, think about this. How well do the Maps applications on your phone work without a network? This isn't just about whether it knows where you are with GPS, but whether it even can determine a route for you to take. Now that we've looked just a little bit at what AI at the edge is, let's look at what makes it so important. Now that you know a little bit about what AI at the edge is, let's consider what makes it so important. We'll look at areas like how network impacts, latency considerations, security concerns, and optimizations for local inference make the edge important. Network communication can be expensive, such as in cost, bandwidth, or power consumption, and sometimes even impossible. Streaming video and audio information in particular to the cloud for processing is especially data intensive. Real-time processing is necessary for applications like self-driving cars that cannot handle latency in making important decisions. If we look at security in the edge, you could be using personal data, like health data. That could be pretty sensitive if sent to the cloud. Business data, such as financial data or proprietary intellectual property, could be stolen if sent to the cloud. Optimization software, especially when made for a specific hardware, can help achieve great efficiency of deployed AI models. In this course, we'll use the Intel distribution of OpenVINO toolkit for this purpose. We'll look at applications of the edge next, where you can start to see even more benefits of edge deployment. There are nearly endless possibilities with the edge. Internet of Things devices are a big use of the edge. Let's go ahead and look at a few of these applications as a brief introduction. As mentioned before, self-driving cars are one kind of edge application. How about detecting irregular heartbeats or heart attacks, or even robots used in surgery? Another application might be tracking animals that are in danger of poaching. All of these are pretty interesting and novel applications of the edge and are only fairly recently possible. The more Internet of Things and wearable devices there are, the further the spread of edge applications. Now, do we need the edge for everything? Not every single app needs it. You can likely wait a second while your voice application goes to ask the server a question. Or when NASA engineers are processing the latest black hole data, they don't necessarily need it right away. Now that we've considered some edge applications, where exactly did the edge come from? You've seen a bit about what the edge is and some example applications at the edge. What about where it came from? From the first network ATMs in the 1970s, to the World Wide Web in the 1990s, and on up to smart meters in the early 2000s, we've come a long way. There's many different devices, such as constantly used devices like your phone, to smart speakers, smart refrigerators, locks, warehouse applications, and more. The Internet of Things pool keeps expanding. Now, cloud computing has gotten a lot of the news in recent years, but the edge is also growing in importance. As this almost absurd looking chart on the left shows, per Intel, Internet of Things device growth has gone from 2 billion devices in 2006 to projected 200 billion by 2020. We've talked a little bit now about what AI at the edge is, some of its applications, and the history of the edge. Next up, let's look at what we're going to do throughout the rest of the course. Now, let's preview the structure of the course and where we'll be heading. We'll largely focus on AI at the edge using the Intel distribution of OpenVINO toolkit. With its pre-built libraries for optimized inference, you can focus more on your edge application development rather than eking out the last bit of speed from a model. In the lessons, first, we'll start off with pre-trained models available in the toolkit's Open Model Zoo. Even without the need for huge amounts of data and costly training, you'll be able to deploy powerful models already created in many applications. Next, you'll learn about the Model Optimizer, which can take a model you trained in frameworks such as TensorFlow, Caffe, and more, and create an intermediate representation optimized for inference with the toolkit and Intel hardware. Third, you'll learn about the inference engine, where the actual inference is performed on the intermediate representation model. Lastly, we'll hit some more topics on deploying at the edge, including things like handling input streams, processing model outputs, and the lightweight MQTT architecture used to publish data from your edge models to the web. Now that we've hit these topics, you might be wondering what the real differences between them are. Let's look at that next. We will hit each of the topics in more detail in the related lessons, but first, let's look at when each of these get used and how they are distinct. Pre-trained models can be used to explore your options without the need to train a model. These will then get used with the inference engine, as they are already in the IR format. This can be integrated into your application and deployed to the edge. If you already created your own model, or are leveraging a model not already in the IR format, such as one in TensorFlow, Caffe, MXNet, etc., use the Model Optimizer first. This will feed to the inference engine, which can be integrated into your app and deployed at the edge. While you'll be able to perform some amazingly efficient inference after feeding into the inference engine, you'll still want to appropriately handle the output for the edge application. And that's what we'll find in the final lesson. Before we dive in, let's cover the relevant tools and prerequisites for the course to make sure you are ready to go. For prerequisites, you should first understand the basics of computer vision and AI model creation. We will not be covering training models in this course, as the focus is on optimization and edge deployment. The other prerequisite is basic Python or C++ experience. Now, the first course is mainly in Python, although C++ can be used with the toolkit pretty easily as well. As you'll see later, plenty of the actual code of the toolkit software is in C++ itself, but we'll interact with it in Python here. For getting set up, classroom workspaces will be available for the exercises, so there won't be any setup required. There are links to local setup instructions in the classroom if you want to work on your local machine. While we won't cover it in this course, another option is to sign up for Intel DevCloud for Edge. Again, you can find the link for this below in the classroom. Intel DevCloud has a wide variety of Intel hardware available, from CPUs, GPUs, and the Neural Compute Stick, so you can try out various edge environments. I do want to note that we won't actually get into the differences between hardware in this course, but we will in later courses. One last thing before we kick off. A brief look at the project you'll build at the end of the course. The project at the end of the course is to develop a people counter app at the edge. First, you'll convert a model to the intermediate representation, use it with the inference engine, process the output to gather statistics, send those statistics to a server, and then perform analysis on both the performance and further use cases of your model. By the end of this course, you'll have all the skills needed to build this project and more. In this lesson, we quickly hit the basics of what the edge is, its importance, and some example applications. We also went over the various topics of the course and how they relate to each other. Lastly, we did an overview of what you'll build in the project at the end of the course. Now, let's get started. In this lesson, we'll cover the basics of the Intel distribution of OpenVINO toolkit, different computer vision model types, the available pre-trained models in the software, choosing the right pre-trained model for your app, and loading and deploying a basic application with a pre-trained model. Let's kick things off with a brief introduction to the Intel distribution of OpenVINO toolkit. The OpenVINO toolkit name comes from Open Visual Inferencing and Neural Network Optimization, not wine. As the name implies, it is largely focused around optimizing neural network inference and is open source. It's developed by Intel and helps support fast inference across Intel CPUs, GPUs, FPGAs, and the neural compute stick with a common API. You can take models built with multiple different frameworks, like TensorFlow or Caffe, and use its model optimizer to optimize for inference. Once a model is put through the model optimizer, you can use it with the inference engine, which helps speed inference on the related hardware. There's also a wide variety of pre-trained models already put through the model optimizer, which we'll cover in this lesson, as well as those later lessons for the other components. So, how does this relate to AI at the edge? By optimizing for model speed and size, this software enables running at the edge. Note that this does not mean an increase in inference accuracy. This needs to be done in training beforehand. The smaller, quicker models the software generates, along with the hardware optimizations it provides, are great for lower resource applications. An Internet of Things device, for instance, doesn't have the benefit of the cloud where it might have multiple GPUs and almost unlimited memory space to run its applications. As mentioned before, there are a lot of pre-trained models available directly in the software. Let's take a quick look at what pre-trained models are and how they are used. Pre-trained models refer to models where training has already occurred. This can lead to high, even cutting-edge accuracy, and avoids the need for large-scale data collection and long, costly training. Given knowledge of how to pre-process inputs and handle the outputs, you can plug these directly into your own app. In the toolkit, pre-trained models refer specifically to the model zoo containing pre-trained models already converted using the model optimizer. As such, you can use these models directly with the inference engine. We've seen this slide before, but here's just a quick visual reminder on how you can feed the pre-trained model directly into the inference engine. Before we get into the full set of pre-trained models available in the OpenVINO toolkit, let's cover some of the basics of computer vision models first. Before we get too deep into pre-trained models, let's look at the types of computer vision models there are. We will mainly focus on classification, detection, and segmentation here. Now, there are other various types or subtypes here as well. Pose estimation or text recognition, for example, might not fit neatly into these categories. Deep learning also has generation of content with GANs as well, although that's not really applicable here. First, let's look at classification. Classification determines a given class that an image or an object in an image belongs to. This can scale from a simple yes/no answer, such as hot dog versus not hot dog, up to potentially thousands of classes like a type of animal. The ImageNet dataset, often used to pre-train neural networks, contains 20,000 classes. The most well-known competition with ImageNet uses 1,000 of these classes, 90 of which are just for different dog breeds. These usually have some sort of probability by class, so that the highest probability is the determined class, but you can also see the top 5 predictions, for example. In detection, this gets used in determining that objects appear at different places in an image. At its most basic, this could be similar to the yes/no classification of whether an object appears at all. Typically, it's more advanced than this, both detecting that an object appears as well as where in an image it appears. Oftentimes, this will draw bounding boxes around the detected objects, so the output may be related to x, y coordinates as well as height and width of the object. Usually, there's some form of classification built on, depending on the network, so that these bounding boxes also note which class they are. These bounding boxes also have a confidence threshold, so you can throw out low confidence predictions. Next up is segmentation. Segmentation classifies sections of an image by classifying each and every pixel. Once again, this can be simple, like road versus not road, or there may be tens of classes, such as road, lane line, grass, tree, sky, pedestrian, you get it. Each and every pixel in the image will be put into a class, although like classification, they may have different probabilities by pixel. Now these are often post-processed in some way to avoid phantom classes here and there. There's also a subset of segmentation to consider: semantic segmentation versus instant segmentation. Semantic segmentation just focuses on classifying every pixel into a given class. So 2 objects of the same class in an image are looked at the same. On the other hand, instant segmentation actually determines objects of the same class to be separate instances. So 2 bikes could be separately tracked through a video. We've looked at different types of computer vision models. Now let's look at some example architectures for computer vision models. Now that we've covered a few types of computer vision models, let's take a brief look at some common neural network architectures used. We'll see that some of the pre-trained models are built with these architectures. The first architecture we'll consider is the single-shot multi-box detector, or SSD. A lot of early detection models would run a classifier many times across an image. The classifier would perform a classification on an image subset, move over a few pixels, then perform another classification. This was incredibly slow. Soon, there was an idea to combine the classifier into an object detection model. SSD worked by having a set of default bounding boxes and using those boxes at different levels of the neural network, thereby using different scales of the image. The ResNet architecture is an architecture known for the use of a residual layer. This residual layer helps pass information forward by skipping in between layers, which also helps during backpropagation during training. These residual layers help avoid what's known as the vanishing gradient problem in very deep neural networks. Backpropagation over many layers tends to eventually reduce the backpropagated error to 0, making very deep networks difficult to train. The residual information held by these skip layers instead allows for these very deep networks to still train. The original paper for ResNet, in fact, itself had 152 layers. MobileNet is an architecture designed originally in thinking of mobile devices, where there are less resources available. This architecture was significantly lighter and faster without the very significant drop-off in accuracy that similar small and fast architectures at the time had seen. This was a bit of a practice in using different types of convolutions to achieve improved efficiency, with the use of depthwise and one-by-one convolutions. Now, these go a little bit outside of the scope of this course, so I encourage you to head to the related link in the classroom if you want to dive deeper. What we've looked at here are just a very small subsample of neural network architectures. There are some more linked in the classroom as well, and many more getting made all the time. Let's head back into the toolkit and see the different pre-trained models available. Most of the models fall into either face detection, human detection, or vehicle-related detection. There is also a model around detecting text and more. Here, we can see some of the documentation on the pre-trained models available with OpenVINO. Up above, you first see the public model set. These models are not yet converted using the model optimizer. So, while you'll have to convert them into the intermediate representation, you also are able to obtain the original models and fine-tune or retrain them as necessary. Further below is the free model set. These models are already converted through the model optimizer, so you can use them directly with the inference engine. However, the original models are not available, so you cannot fine-tune them or train them further. As we move down the page, you can see the different categories available. Up here, you see that there's age and gender recognition, text detection, and further on, you see some of the face detection models, of which there are multiple. Here are the human detection models. And at the bottom of the page, we'll be able to see that there's also different models available for vehicle feature recognition. Within each of these, if you click on a given one, you'll be able to see additional documentation for how to use them, an example of the output, as well as information about the inputs and outputs. Now, using this documentation, you might think, great, these models are available, but how do I get them? On this page, you see an overview of the pre-trained models again, and this will actually give you the exact model names, as well as some additional information as to what activities they do. At the top, there's some details on the model downloader. So here you can see that there is the OpenVINO installation directory, which for me was opt/intel/OpenVINO, as well as the rest of the path here. Within this directory, you'll find a downloader Python file, which you'll be able to use in the upcoming exercise in order to download these different models. Before you get into this, realize that many OpenVINO scripts have different arguments that get fed into them. The downloader Python file, you can use a -h argument with the file and see all the different arguments that can be fed in. Using the -h argument is a hint towards what you might want to use in the upcoming exercise. Before you get hands-on with these models the first time, let's consider them in the context of the types and architectures we discussed earlier. The age and gender recognition model is a good example of classification. It attempts to classify the gender of the person in the image. Pedestrian detection is drawing bounding boxes on every detected pedestrian, a good example of object detection. Lastly, the advanced roadside identification model classifies each pixel into one of 20 classes and is a great example of a segmentation model. As far as architectures go, SSD and MobileNet are fairly common throughout the OpenVINO toolkit pre-trained models. Some of them are just using a single-shot detector, others use just MobileNet, and some are using aspects of each. Next up, you will get a chance to practice using the model downloader to get the desired models for your applications. Great work on this exercise. Hopefully, you were able to see how quick it is to obtain different pre-trained models for use in an app. Now, there's some wiggle room as to which models you may have chosen here from OpenVINO. Using the pre-trained model list, you can look at each, and some of these have a pretty specific model that makes sense. The human pose estimation and text detection models only had a single model really available for them. Pose estimation, you maybe could get away with something around face detection with the orientation of a face, but that doesn't necessarily get you the full body. Determining car type and color is a little more advanced, so let's look back at our list. If I'm looking at vehicle feature recognition models, I can look at each and see what might make sense for this data. The one that stuck out to me was the vehicle metadata one, as I can see that I can get color and type here. There's a few different colors and a few different types, mainly just whether it's a car, van, truck, or bus, not necessarily what model or brand it is. So let's look at each of these models here. I've now clicked on the pose estimation model that was available in the first documentation page, and what's actually at the top is the model name. This is pretty important for what we're going to do with the model downloader. So here I'm in the workspace in home, and we mainly want to make sure that we are actually in the correct directory where the model downloader is. So let's first cd to there. And I'll make this a little better for you all. Now if I check what's in here, I can see that the downloader file is available here. Now if I want to see the arguments available, I can use the -h command to see these. There's a few that stick out to me here. If I come up and see the -- name, that's the name that we just saw for the pose detection model. As part of the assignment, you were also asked to use certain precisions of models. So this is what the -- precision is used for. Now when you run the model downloader, you'll want to use the sudo command with this, as it's otherwise installing in a directory that you won't have access to without it. So you can use this sudo /downloader.py, and you'll want to use the -- name with your model name. In this case, we just have human pose estimation. Now if we look back in the instructions, we can see we wanted all precision levels. This means we don't need to feed an additional argument. Great, so now the human pose estimation model has been downloaded, and there's multiple precision levels, as you can see here: floating point 32, floating point 16, and int 8. Now the process is actually pretty much the same for the other two models. So what we want to do is make sure that we go and find their names. Here's the text detection model. We'll put that there, and we also want to add precisions. And in this case, we just want FP16. As you can see in the downloads, only the FP16 model was downloaded. Now for the final model, we'll want int 8, so we can replace that. And let's delete this name. And here is this final model name. Paste it in, and just the int 8 models have been downloaded. Now to verify that these models were downloaded, it's actually in this same directory essentially. We'll cd first into Intel, and you'll now see that there are directories for each of these models. And if we look at a single one, there's going to be our different precisions. And if we just go into a single one of the precisions, we can now see the available models, a binary file, and an XML file. So if you have all of those models available in your directories, that means you have successfully downloaded the models. You may be wondering at this point what some of the optimizations are on these different pre-trained models. How are they being made more efficient for edge deployment? In the exercise, you've dealt with different precisions of the different models. Precisions are related to floating point values. Less precision means less memory used by the model and less compute resources. However, there are some trade-offs with accuracy. There is also fusion, where multiple layers can be fused into a single operation. These are achieved by the model optimizer typically, although the pre-trained models have already been run through that process. We'll get into more of these optimization techniques in the next lesson, but I wanted to make sure that you already have an idea of how these models are an improvement on just running a model straight out of training. In the exercise using the model downloader, you spend a little bit of time considering which model to use given certain tasks. I want to talk a little bit more on this, as well as the inverse. Given a model, what are some additional applications you could build, perhaps unrelated to the original intention? This will be a little high level. And it's not necessarily the case there is an exact answer. You should try out different models in your application and compare and contrast their uses. For example, considering the different face detection models available, there seem to be a lot of ways to consider the direction someone is looking. Let's consider you had a console game that wanted to use eye tracking to allow someone to choose options or actions with their gaze. The standard face detection model looks like it gets the direction of a person's head pretty well. And then there's also a facial landmarks model that gives a little bit more detail about certain aspects of where a person's face are, but maybe not the direction without further processing. There's also a head position model that seems closely related. Here, I'd consider testing each of these against each other and see which better suits my needs. Note that these models are actually only tracking head position and not gaze, so there may actually be an even better model out there to fit here. There are plenty of ways to think outside the box on additional use cases for the available pre-trained models. Here are just a few I thought of. You could use the people, vehicles, and bikes model to assess traffic coming into your store. This could allow you to learn more about what types of items people might buy, such as those people on bikes probably aren't bringing TVs home. It could also inform you about changes needed to your parking lot to allow for more bike or motorcycle parking. The pedestrian attributes model could be used to identify the potential for altercations amongst rival sports fans with different jerseys, allowing security to step in ahead of time. The human pose estimation model could be used for a wide variety of augmented reality apps, whether trying on clothes or even showing your friends around you dressed up as warriors for a video game. It could even be used in physical therapy to see the range of motion of an injured limb. Once you have decided on a model, in order to implement it in your application, you'll need to pre-process any inputs to fit what the model expects. The pre-processing needed for a network will vary, but usually this is something you can check out in any related documentation. First and foremost, it can even matter what library you use to load an image or frame. OpenCV, which we'll use to read images in this course, reads them in the BGR format. You may have heard of RGB before, or red, green, blue. This just means the order is blue, green, red with OpenCV when loaded with cv2.imread. Many pre-trained models will use this format as well. Outside of channel order, you also need to consider image size and the order of the image data. Image data may have the color channels first or last, with the height and width as the other dimensions. Certain models may require a certain normalization of the images for input, such as pixel values between 0 and 1, although some networks also do this as their first layer. I'm back in our documentation for the human pose estimation model, and within it, we can see there's a section about the inputs. The first thing you note is the shape. So the 256 by 456, we can see our height and width, and then in this case, the channels actually come first. There's also a dimension of 1 at the start for batch size, so that's something important to remember for the upcoming exercise. The last piece of this to see is that the color order is BGR. Now our OpenVINO pre-trained models are going to be using BGR by default, and OpenCV, which we'll use to load images in the exercise, also uses BGR. So you won't need to do any pre-processing, in our case, on the images to change from RGB to BGR. Before the coming exercise, where you'll perform pre-processing for our 3 models from earlier, I want to briefly hit on a couple useful OpenCV functions. First, you can import cv2 to use OpenCV in Python. Then you can use cv2.imread to read images in BGR format and cv2.resize to resize them. An important thing to note with cv2.resize, while normally when dealing with arrays like an image, you're used to seeing rows by columns or height by width. With resize, you want to feed in width first and then height when you resize. Since the image frame will basically be a NumPy array, you can also use array functions like .transpose and .reshape on them as well. useful for switching the array dimension order. Note that OpenCV can also convert from one color space to another, such as if you had an RGB image and needed BGR. We'll talk more on OpenCV in a later lesson, so you can work with additional pre-processing steps and other techniques. Awesome job on this exercise. Learning to read documentation and appropriately pre-process image inputs is a really important skill to have to work with pre-trained models. Back in the workspace, first, we have the links to each of our models here, which we'll need to use in order to create our pre-processing. Now, there's a separate function in here for each different model. Depending on exactly what the pre-processing is, it might be very different depending on which model is used. Let's start at the top with pose estimation. And to get started, we'll move back to its documentation to see what we need to do. Once again, here are the inputs for this model. We see first that it's a 256 by 456 image. And the channels need to be first, and then we have that one dimension for batch size. So I'll start out by using cv2.resize to match the size that we saw in the documentation. Now, if you remember what I said earlier about this resize function, is we actually want the opposite order from height by width. So instead, I want to make sure that I put this as 456 by 256 to resize it. The next step is to transpose this so that the order has channels first, because our image after resizing still is going to have channels last. So, because it's an array, we do this operation here. We'll first put the third channel, which is actually our image channels for BGR, and then next is 0 and 1 for our first and second, which were originally our height and width of the image. And then lastly, we need to do just a basic reshape. Now this is to add that one dimension at the very start. And so we add that here. We put 3 now that our channels are first because of the transpose. And this time we actually will do height by width. So note that this, unlike earlier on, will actually have the height first, whereas width and height in cv2.resize. And for our pose estimation, this is actually going to do it. So if we're in the directory here, we do have a test file we can run. So let's run that and see whether we have done the right processing for pose estimation. And as we can see, we've already passed the pose estimation test. We haven't implemented anything yet for text and car, so we didn't pass those tests. An interesting thing, if I come over to the documentation next for text detection, is that we're actually going to use the exact same operations. We'll need to resize, and the order again is batch size by channel, by height and width, and the expected color order is BGR. In fact, if I jump next to the car documentation, this is going to be similar again. Note that there's the one here. It doesn't show the batch size here, but it's going to be one once again. So that means we can actually reuse our code. Since we can reuse our code, let's actually make a separate function here. And it looks like we will want our input image as well as a height and width. Now within that, let's actually copy our operations from before, put them in, and we'll say that image is our input image. And this, remember, for resize, is the width and height. And let's just go ahead and use image for each of these. And make sure here to use height and width. And we can just return our image. So in pose estimation, let's go ahead and cut out most of this. And remember that it's 256 by 456. With our pre-processed image and 256 and 456. Save that, and let's run the test one more time to make sure this is still correct. And we passed again. So this actually greatly simplifies what we need to do on the other two models. We basically can just add this line and the right height and width, and we'll be able to pre-process them. So I'll put those here real quick. Let's go get the input sizes from the documentation. So text is 768 and 1280. And our final one for car is 72 by 72. And I have to make sure to save this. And now all three tests have passed. Now that we've pre-processed our inputs, we're ready to feed it into the inference engine. You are just about ready to put a pre-trained model into an edge application. However, now that we've appropriately pre-processed the inputs, we also need to appropriately handle the model outputs. Like the inputs, you can also see the outputs for any given model within its documentation. One of the typically easier outputs to handle are those from classification models. If we take a look at the motion recognition model, we'll see it's just a 1 by 5 by 1 by 1 array. This is just the softmax classifier for the 5 emotion classes available. If you have an array that maps the motion names back to this classifier, you can use the argmax of the output to grab the most likely class. Networks that output bounding boxes will have varying outputs, but they usually note something on the number of boxes, class, confidence, and at least one XY pair. Then they usually also have a height and width of the box or a second XY pair to draw the box. Note that these boxes need to be scaled if the image was resized for input into the model. The pedestrian detection model is a good example of this. The output is 1 by 1 by n by 7, where n is the number of bounding boxes. On the other hand, the 7 is made of image ID, label, confidence, xmin, ymin, xmax, and ymax for each bounding box. At the end, for post-processing, you may want to throw out some detections that have a low confidence threshold. For a semantic segmentation network, the output will be some form of the class by pixel. Some may be flattened and need to be reshaped to be mapped back to the original image. Others may need to be scaled up to the full image size. Taking the advanced roadside identification model as an example, the output is batch size, height, and width. In this case, the output is the same size as the input, so you can map the pixels of this output directly to classes in the input. Now that you know a little bit about handling the outputs, let's get you prepared for running your first edge application. You are now ready to add a pre-trained model into an existing application. There's a few items for us to consider as we get your first edge app running. We covered the key parts of working with a pre-trained model: obtaining the model, pre-processing inputs for it, and handling its output. In the upcoming exercise, you'll load a pre-trained model into the inference engine, as well as calls for functions to pre-process and handle the output in the appropriate locations from within an edge application. Now, we'll still be abstracting away some of the steps of dealing with the inference engine API until a later lesson, but these should work similarly across models. Let's take a moment to look at the exercise code here before you get started. This has a little bit more than some of the exercises we've worked with so far. Here in Handle Models are each of the functions you'll implement to handle the output of each different model. Once again, we have separate functions for each of the models. This time around, it won't be as easy to use the same processing as we did with pre-processing. Within here, there's actually a function so that you can use this with a model type that will be an argument within the app. Each of these will return one of these functions, and you can then use this function directly within the app. At the bottom of this file, I've also carried over our pre-processing code from before so that you don't have to re-implement this again. However, you will need to call it from within the app. Inside our app, you'll notice at the top the getArgs function. This will take command line arguments. We can see the descriptions of each here. The first is a CPU extension file, which you don't need to concern yourself with too much, as we'll give you the instruction here in the workspace for which CPU extension to use. Next up is the device, if it's not CPU, as the default that we've set below is for the CPU. From there, the app needs to know the location of our input image for testing, the location of the model XML file, as well as the type of model. Again, we use this type of model to help determine which of those output processing functions to use. Down below, you can see that the image, model, and type are all required. The CPU extension I didn't mark as required, although here in the workspace you'll need to use it. If you wanted to use this outside of the workspace or with different hardware, you potentially would not need this extension. There's also code here for get mask and create output image, which does just a little further post-processing from what you need to do in handle models. You don't need to worry too much about this code, but I do encourage you to read through it to see what some of the other code is necessary to get an output image showing our semantic masks, as well as outputting our classes directly onto the image. The perform inference function is used to actually perform inference. It's going to create our inference network, which is in a separate inference file. This is called inference.py, and you can actually access it within the folders on the left. You don't have to worry about this code yet. This is code for working with the inference engine, which we won't work with directly until later lessons. But if you want to get a head start, you can check out that file. This will read in our image. You'll need to add the pre-processing function here for the image. And then it will perform synchronous inference on the image. It will then extract the output, and it will be up to you to process that output with the functions you implement in handle models. At the end, it'll feed in to the function that's already implemented here in the app for creating the output image and save down the resulting image, so you'll be able to look at the results of your code. Now it's time for you to get started on the exercise. I'm really excited to see the results. Amazing. You now have a running edge application, all working with high efficiency pre-trained models. You didn't even have to use your own data set and network to accomplish this. In my own approach to this exercise, the first thing I focused on was adding the pre-processing. Here in handle models, I have my pre-processing function. I'll go ahead and just copy this real fast. And I can note in this code that the image is actually called image here, so I'll change that. And up above, I can see that it's actually H and W for height and width from our model. So I'll shorten that down. And that's actually it for implementing the pre-processing there. The next step is to actually handle the processed output. Now, one thing I'll consider here is looking back and using this helper function to get that function. The nice thing is all the functions above use the same inputs of output and input shape. So this function can behave the same way back in our app. I'll paste that in, and here, because that was our argument, is actually args.t to get our model type. And actually, this isn't really our processed output. This is our process function. So let me set that. Now, the interesting thing here is this process function is dependent on this model. So again, back here, this selects which of our functions above. We have the same inputs for each. So we can set this with our output, which is the correct name. Our input shape is actually going to be image.shape here in our code. So we've actually implemented just about everything we needed to do in the app. Now we need to implement our functions and handle models. The first thing I want to do actually is figure out just what those outputs actually are. So I'm going to change up the code here just a little bit and first add a try function. Because otherwise, if I feed an invalid input here to this function, it's going to crash. And what I'll do is just set the output image to our original image if there ends up being an error, and let's just add a print function as well to know whether this completed successfully or not. Back in handle models, let's start first with the car model. This has kind of the simplest output, so it'll be the easiest to handle. If I go back to the documentation, below our inputs, we get a little bit of data about the outputs. Here it tells me there's color and type and a shape, but I don't know exactly how that comes back to me. So here, to start, I'm actually just going to go ahead and print the output as well as the output.shape. Actually, I think that getting the keys will probably be the easiest thing, as from the OpenVINO documentation, usually the output is coming back sort of like a dictionary. So this will give me what the names of these outputs are. Now, if I want to run the app, we mentioned there were quite a few arguments. Here, I've actually put in an example of this somewhat long code to use. And here, let's just cover this real fast for the first time of doing it so that we know exactly what's going on. Our first argument is our image. If we look in our directory, we can see the images here and actually see this blue car image. Let's look at that real fast. And we can see that we clearly have a blue car, and this image is going to get passed into the model. I've also set the type to car meta, and then the model path here, which is pretty long. Again, you might actually consider dropping this in a different directory when you work with it, just so it's easier to access and you don't have to use this full OpenVINO toolkit path each time. The -C then is our CPU extension, which, as I mentioned, is something that is provided for you here. You don't have to worry about it too much until we actually get into the inference engine later on. I'll actually do the output.keys first. I'll want the shape of what I get from each output as opposed to using the shape here. So if I run our code here, I will get my error output as we expected because we haven't implemented this function yet, but we also get these dictionary keys. The first one is color and the second one is type, which matches actually to what the documentation told us. So back in our code, let's go ahead and make a color that is our output with color, and we'll do car type as output with type. Now, before I move too far again, I actually do want to get the shape of these, which I hope should match what we saw in the color in the documentation. And it does. We get 1, 7, 1, 1, 1, 4, 1, 1, and that matches to what we saw before in the documentation. So one thing I'm actually going to do first, because we notice that they have all these extra dimensions of 1, is use .flatten on these. So that will get rid of those extra dimensions. And then we can actually go ahead and use the argmax on each of these and return those. So let's go ahead and get color class, which we'll go ahead and say is the NumPy argmax of color, and the type class, the NumPy argmax of car type. And we just need to return both of these. And see what happens. Let's run the app again. So we got success. So that's good. Let's check back here in our outputs folder to see what happened. So now we can see it's actually output correctly that this is a blue car. Great. So now we have one of our models handling the output appropriately. Now that we've handled the car output, let's go ahead and handle the pose output. First, I'll start in a similar fashion. I want to make sure that I actually know what's in our output. So I'm going to get the keys. Now I do need to make sure that I update what's here in the path and what we're going to use. So here I've updated the text. This is using the sitting on car image, which is for our pose. And here again, the type is set to pose, and I've updated our model path to use this model. So I'll run it. And we can see from the output, again, we got an error. It's not implemented. But we can actually now see these two names. Now, these don't seem super useful, although in our case, the second blob output is actually what we want. Here in the human pose estimation documentation, we can see the second one contains the key point heat maps, which is what we actually want to use in our case. This will make the output potentially a little weird looking, as we're only drawing the heat maps around things like joints and ears and eyes and such, as opposed to drawing the lines that connect them all for your pose. But this simplifies a little bit about what you have to do here. Now that we have our keys, we know that our output is actually the second key here. So I'm going to copy that in and extract it. It's our output with our key. It's a bit weird name, but this is what we'll get it from. Once again, I'm actually going to print the shape of this just to make sure that it matches to what I expect. And here I got the 1 by 19 by 32 by 57, which matches to what the documentation said. Now this might sound a little weird because you're thinking, okay, what exactly is this? And that's why it's important always to pay attention to what the documentation says. Here in the outputs, we don't necessarily know much about what the shape is. However, if we go back up the page a little bit, we can actually see that these key points are the ears, eyes, nose, etc. that are the different points. The important piece is here, we need to resize it to the right size. So let's actually feed this in. So I've added in some of my processing steps here, and let's just walk through them real fast. So here, I want to actually iterate through and resize each of these of the 19 layers that we get as the output. Now this is pretty important because cv2.resize actually only takes dimensions of 1 or 3 for the channels, which is usually a color image or a grayscale image. In our case, because there's actually 19 of these layers that are sort of like channels, it won't know what's happening. So what I did was actually just iterate through the full 19 of these one by one and resize them. Note that to make sure I'm getting the right size here, I actually am using the different shapes and such. So the input shape here of 0 to 2 is basically just cutting off the very end of it and then reversing it so that we make sure that we get the width and the height. Up here, this is actually just an array so that I can put the outputs of the resized layers up here. If I don't have that and try to do it in place, it would cause an error, as you'd be trying to resize a portion of an array and not the whole thing at once, and CV2 would not know what you're trying to do. With this, we can return our out heat map, which is this that has been filled by the resized outputs, and we'll get success. Here I can check my output for pose. I'll put that up here. And while it looks a little silly, you can actually see that things like the shoulder, the elbow, the wrist, the knee, etc. are marked in green with the heat maps. And if we had also used the other output, we could potentially draw the parts between them to show exactly the functionality of different limbs and such. All right, final one. Let's look at how to handle the text output. So now I've placed in my solution for handling text. This is actually a pretty similar approach, as there's two output classes here. So I want to go ahead and do the same iteration. Although in my case, there's one thing to consider, which is that the outputs are text versus not text, and the second one is text. If you go back into the app, you'll actually find that it gets processed that way to ignore the no text layer, and it's only looking at the detections related to text. So we can now run this. We get success. So let's go check our output. Here's my text output. And if I pull it up here, we can see this sign says, "You got this," is now in green, and nothing else in the image is. So it looks like it's now working. In this exercise, you got some great practice with an example edge application. It's pretty simple so far, just using a few test images and a few models, but you already have some amazing skills able to pull in a pre-trained model that you did not have to do any training or data collection for yourself and already deploy an app. In this lesson, we covered the basics of the Intel distribution of the OpenVINO toolkit, the different computer vision model types, the available pre-trained models, as well as choosing the right pre-trained model for your app, and finally, loading and deploying a basic app with a pre-trained model. I'll see you soon in the next lesson when we discuss the model optimizer. Welcome back. In this lesson, we're going to cover the basics of the model optimizer, some of the different optimization techniques and their impact on model performance, the supported frameworks in the OpenVINO toolkit, as well as converting from models in those frameworks to intermediate representations. At the end, we'll also cover a little bit on custom layers. Let's kick this lesson off by looking into the basics of the model optimizer. The model optimizer helps convert models in multiple different frameworks to an intermediate representation, which is used with the inference engine. As part of the process, it can perform various optimizations that can help shrink the model size and help make it faster. Now, if you're not using one of the pre-trained models we covered in the last lesson, this is a required step in order to use the inference engine. An important thing to note about the model optimizer is that it does not improve accuracy. In fact, there's sometimes some loss of accuracy as a result of changes like using lower precision. However, these losses in accuracy are minimal. We'll actually look a little more in depth at some optimization techniques in a subsequent video. Configuring the model optimizer is pretty straightforward, given that you already have OpenVINO installed. You can navigate to your OpenVINO install directory first, which for me was /opt/intel/OpenVINO. Then you'll go to Deployment Tools, Model Optimizer, and the Install Prerequisites directory. If you are only interested in working with one framework, there are also separate scripts for each. However, it's easiest to just run the main Install Prerequisites script, which will install all the prereqs for all supported frameworks. Now that we have the model optimizer configured, let's look at a few of the different optimization techniques that might be used. We've mentioned a few times that there are different optimization techniques at play with the OpenVINO toolkit and the supported frameworks. Let's look at a few of these, including quantization, freezing, and fusing. Back in the first lesson, when you downloaded different pre-trained models, you downloaded certain precisions of these models. Quantization is related to this topic of precision, or how many bits are used to represent the weights and biases of the model. During training, having these very accurate numbers can be helpful, but it's often the case in inference that the precision can be reduced without substantial loss of accuracy. Quantization is the process of reducing the precision of a model. With the OpenVINO toolkit, models usually default to FP32, or 32-bit floating point values, while FP16 and int8 for 16-bit floating point and 8-bit integer values are also available. int8 is only available in the pre-trained models, as the model optimizer is not able to create that level of precision. FP16 and int8 will lose some accuracy, but the models will be smaller in memory and the compute times faster. Therefore, This is a very common method used for running models at the edge. Freezing, in this context, is different than what you may normally think of as freezing in training neural networks. In training, this usually means freezing certain layers so that you fine-tune and train on only a subset of layers. Here, this is being used in context of an entire model and is related to TensorFlow models in particular. Freezing TensorFlow models will remove certain operations and metadata only needed for training. For example, backpropagation only exists for training purposes. It is not used for inference. Freezing a TensorFlow model is usually a good idea, whether before performing direct inference or converting with the model optimizer. Fusion relates to combining multiple layer operations into a single operation. For example, a batch normalization layer, activation layer, and convolutional layer could be combined into a single operation. This can be particularly useful for inference. The separate operations may occur on separate kernels, while a fused operation occurs on a single kernel. This will then incur less overhead in switching from one kernel to the next. There are a wide variety of optimization used in the software. Some depend on a given model or layer, such as the automatic fusion of certain layers like linear operations. The ResNet model in particular also has some of its own optimizations. Check out the link in the classroom for some more information on the specifics of these. Of course, there are also the different precision levels you choose when using the model optimizer. There are also certain hardware-specific optimizations that can be done, although those will be covered in the later courses. There are quite a few deep learning frameworks supported by the OpenVINO toolkit for use with the model optimizer, so let's check those out. Here are the supported frameworks that work with the model optimizer: Caffe, TensorFlow, MXNet, Onyx, which can actually support PyTorch and Apple Core ML models through another conversion step, and Caldi. Now, you may not be familiar with all of these, but that's okay. Hopefully, the one you want to use is listed here, or otherwise supported with an additional step like PyTorch with Onyx. All 5 of these are open source frameworks. Caffe is originally from UC Berkeley, TensorFlow from Google Brain, MXNet from Apache Software. Onyx is actually a combined effort of Facebook and Microsoft, and Caldi was originally an individual's effort. Most of these are fairly multi-purpose frameworks, while Caldi in particular is primarily focused on speech recognition data. We'll cover how to use the model optimizer with a few of these coming up, and then you'll get a chance to use them yourself. Note that there are some differences in how exactly to handle these, although most differences are handled under the hood of the software. For example, TensorFlow has some different steps for certain models, or frozen versus unfrozen models. Certain frameworks have additional optional parameters you can feed to the model optimizer. However, most of the functionality is shared across all of the supported frameworks. We've seen intermediate representations a few times throughout the course so far, but we haven't really gone in depth on what exactly they are. Let's look into these, including some of the conversions that happen from the original model, as well as the output files of the model optimizer that make them up. Intermediate representations are sort of like a shared dialect of neural network layers from all the supported frameworks. A conv2D layer in TensorFlow, convolution layer in Caffe, or conv layer in Onyx are all converted into a convolution layer in the IR. At the bottom of this page, you can see more of how different layers translate over to an intermediate representation. There's also a link where you can read more documentation specific to these layers within the IR itself if you're interested. Any of the desired optimizations available will have occurred while this is generated by the model optimizer, such as changes to precision. The intermediate representation is then able to be loaded directly into the inference engine. The intermediate representation is actually made of 2 output files from the model optimizer, an XML file and a binary file. The XML file holds the model architecture and other important metadata. The binary file holds weights and biases in a binary format. So you'll need both of these files in order to run inference. These will be generated for the precisions you specified to the model optimizer with a -- data type argument, which is usually floating point 32 by default. Next up, let's begin looking at how to convert models from the different supported frameworks. We've been talking about the model optimizer for a while now, so I'm sure you are ready to get your hands dirty with it. We're going to walk through how to do so with TensorFlow, Caffe, and Onyx here over the next several pages, as well as letting you work through the exercises to do so for each. First, it's important to note that each framework has its own documentation page or pages concerning conversion, although the process is very similar throughout. In most cases, you will run the model optimizer Python file with somewhere from 0 to a few additional arguments outside of the model itself and get your intermediate representation. The first thing to do is make sure you ran the configuration steps earlier, either for all models or specifically for TensorFlow. The Classroom workspace already has this step done for you. Next, you will need to either freeze your model, which I would suggest, or use the separate instructions in the documentation to convert a non-frozen model. Some models in TensorFlow may already be frozen, and if so, you can skip this step. From there, you can feed the model into the model optimizer and get your intermediate representation. There may be a few items specific to TensorFlow for that stage, which we'll cover in a second. Finally, I'd suggest testing the model using the inference engine itself. There are plenty of demo applications for different models available on the OpenVINO toolkit website, which can be helpful if you don't have an application to use it for just yet. TensorFlow models can vary for additional steps needed by model type, being frozen or unfrozen, or being from the TensorFlow detection model zoo. Unfrozen models usually need the -- mean values and -- scale parameters fed to the model optimizer. This is also a concept for the other frameworks, but unfrozen models in particular very often require these. The frozen models from the object detection model zoo don't need these parameters, but they will need TensorFlow specific parameters like -- TensorFlow use custom operations config, as well as the object detection API pipeline config arguments. Also, the -- reverse input channels argument is usually needed with these models, as they are trained on RGB images, while we'll be using OpenCV and loading as BGR. Certain models like YOLO, Deep Speech, and more have their own separate documentation pages. Now, TensorFlow is really the more complicated of these frameworks to use with the model optimizer, just because of some of the complexities we saw earlier on. I wanted to take a quick moment to discuss the TensorFlow Object Detection Model Zoo. This can be used to even further extend the pre-trained models available to you. However, it's important to note that these are in the TensorFlow format, so they need to be fed to the model optimizer to get an intermediate representation. These models are just focused on object detection with bounding boxes, but there are plenty of different model architectures available. You will use one of these models in the upcoming exercise, and it's also linked to below in the classroom. So here, I have the Converting to TensorFlow Model documentation page up. There's a lot of useful information here, such as the steps we covered earlier of configuring, freezing the model, and then converting over to IR, testing, and integrating your app. Down further below, there's lists of the different supported topologies of different types. Here you can see the frozen models that are available in the object detection model zoo. And then here on the left, you can actually see there's additional TensorFlow documentation pages, such as the one for YOLO, FaceNet, Deep Speech, and then the specific one for the object detection API models that you'll want to use for the exercise. In the exercise, you'll get a chance to download one of the models from the TensorFlow Object Detection Zoo, and then convert that to an intermediate representation with the model optimizer. So now, we'll go ahead and look at the way I approach this exercise. I'm here in the exercise workspace, and the first step I'll do is just get my link address for the model, and I'll use wget to download it into the workspace. Great, so that's here, and I actually want to use this tar command to extract it. Once it's extracted, go ahead and cd into there. And from within here, we can see there's a few files. The one that's really most important to us is this protobuf file that's the frozen inference graph. And then if you remember from the commands for TensorFlow, we'll also want this pipeline config file. So here's the command I'm going to use, which looks like a lot, but let's just break this down. First, this path is just to the model optimizer file in OpenVINO. The next argument is the input model, which again is our frozen inference graph. Following that, we want to feed in our pipeline config file for these object detection model zoo items. And remember that we also want to reverse the input channels since they're RGB and we want BGR. This last one is a little trickier with TensorFlow use custom operations config. This is within the documentation that we were looking at earlier, and this is how I found where it was. So it's within the model optimizer, adding an extension to the front of the model within TensorFlow. And because we're using an SSD model, because we're using the SSD MobileNet v2 model, we're going to plug in this SSD v2 support JSON file. Now if I run this, it's going to give me a little information. You can see because I didn't feed a different precision, we're using floating point 32. Great. So now the model optimizer has finished. There's a few important items of information to consider here. First, the preprocessor block was removed. So you'll need to consider that for your inputs to this model. Further down, we can see it successfully generated the IR model, created an XML file and a binary file, as well as the locations of those. We can see here it took about 66 seconds to do, and this is because the model is a little more complex. We'll see with the later models they don't take quite as long to process. Lastly, you can just verify within the directory that here's our XML file and our binary file that we'll be able to use with the inference engine. Great job converting the TensorFlow model into an intermediate representation. Now we're going to move on to cafe models. Now that you've gone through the process with TensorFlow, let's next look at converting a model with cafe. Here are the steps for converting a cafe model. You may notice the process is pretty similar to the TensorFlow one, although there's nothing about freezing the model this time around, since that's a TensorFlow specific concept. Again, if you haven't already, you first run the configuration steps from earlier, either for all models or just specifically for cafe. The Classroom workspace already has this step done for you. From there, you can feed the model into the model optimizer and get your intermediate representation. There may be a few items specific to cafe for that stage, which we'll cover in just a second. Finally, you should again test your converted model using the inference engine itself, including some of the demo applications on the OpenVINO toolkit website. So, what are some of the differences in converting cafe models versus the other frameworks? Well, I already mentioned there's no need to worry about frozen or unfrozen models in cafe like you do in TensorFlow, as there's no such concept in cafe. There's also a different set of supported model architectures with cafe. You'll feed the cafe model into the model optimizer, and if the prototext file has a different name than the model, it should be fed in with a -- input proto argument as well. Next up, you'll apply these steps in order to convert a SqueezeNet model in cafe to an intermediate representation. Just like we did with TensorFlow, let's first look at the documentation for cafe. Here on the cafe page, you'll notice there's some pretty similar topics here. However, there's no additional pages under cafe like we saw with TensorFlow. We'll start with the steps, and then here is a list of supported topologies. And in fact, we'll be using one of these topologies, SqueezeNet, soon. Nice work. You've now converted a cafe model into an intermediate representation. I'll go ahead and show you my approach to this problem. Here in the workspace, I'm going to first download this SqueezeNet model by cloning this repository. Now that I have this repository, if I go into that directory, I can see that I want to use this v1.1. And here, I'm in the v1.1 directory. and we can see that I have a cafe model here. Although notice that I don't have an exact matching proto-text file with this name. So that means I'm going to need the -- input proto argument when I use the model optimizer. So here's my command for working with the model optimizer with our SqueezeNet cafe model. Once again, it starts out with this somewhat long path to the model optimizer file, the input model, which is just SqueezeNet v1.1, and then because it doesn't have the same name of the proto-text file, I have to feed the input proto argument. Once I run that, this will come in. One thing I noticed as it came up was that it said that if I want to actually run this model, I need to have an update of protobuf. So that's one thing that you might notice as you run the model optimizer, is libraries you might need to update. At the end here though, it shows that again, I successfully generated the IR model. This time it was significantly faster than with the complicated TensorFlow model, as it only took 3 seconds. And I can verify that I have my binary and XML file. Great, now we're through both a TensorFlow and cafe model. Let's move on to ONNX models. Now, we're going to move on to working with ONNX models. As a reminder, PyTorch and Apple Core ML models are pretty easy to convert to these ONNX models as a first step before the model optimizer. I've added a link in the classroom related to converting PyTorch models to ONNX, so you can go check it out. Here are the steps for converting an ONNX model. Really, the only change from the cafe model conversions is that ONNX does not have any specific arguments to the model optimizer just for its framework. You'll only have the general arguments for items like changing the precision. Just to cover our bases here, let's again consider the differences from converting TensorFlow or cafe models. Again, because it's a TensorFlow specific concept, there's no frozen or unfrozen models to deal with in ONNX. Again, there's a certain set of supported model architectures. As we mentioned, there's no specific arguments to the model optimizer. Although if you're working with PyTorch or Apple Core ML models, they need to be converted to the ONNX format first. This is done outside of the OpenVINO toolkit. Just like the last two, let's go ahead and take a look at the documentation for the ONNX models first. So once again, here's the ONNX model documentation. It's going to look fairly similar, and again, we'll start out just with the public topologies. In fact, this very first one of BVLC AlexNet is what you'll use and convert into an intermediate representation in the exercise. Coming up, you'll get to work with the ONNX models yourself in the next exercise. Once again, we're going to go back into the classroom workspace and work with ONNX models. To start, I'll go ahead and download my BVLC AlexNet model from here using wget. And then I need to unpack it with tar once again. Once that's done, I'll go ahead and cd into the directory and just check out what's here. You can see pretty quickly that our model.onnx file is in there. This time, we have the shortest line yet. It starts with just our model optimizer file once again, and it just needs our input model. Once I run that, we'll be able to see it already generated the IR model. Both the XML and binary files were created, and the execution time, again, is very short. And just to confirm, here's our binary and XML file. Great work in that exercise. You've already shown great skills in working with the model optimizer and converted models from 3 different frameworks. Next up, we'll move into a few more advanced topics in using the model optimizer. Next, let's look at cutting parts of a model. This is getting into some of the more advanced but still very helpful features of the model optimizer. To start, why might you need to cut a model? This is mostly for TensorFlow models. As we saw earlier in converting these models, they sometimes have some extra complexities. Some common reasons for cutting are that the model has pre- or post-processing parts that don't translate to existing inference engine layers, that the model has a training part that is convenient to be kept in the model but is not used during inference. It may be that the model is too complex, with many unsupported operations, so the complete model cannot be converted in a single shot. The model might be one of the supported SSD models where a post-processing part needs to be cut off. Or there could be a problem with model conversion in the model optimizer or with inference in the inference engine. And in order to localize the issue, cutting the model might help to find the problem. There's two main command line arguments to use for cutting a model with the model optimizer. These are going to be input, which as you might guess is for new entry layers, as well as output, which is for specifying new end layers. We won't delve too much deeper in this course on cutting a model since it's a more advanced topic. However, if you think you'll need it, or just want to try it out, make sure to check out the documentation linked below in the classroom. Let's finish off this lesson with a couple of related advanced topics: supported layers and custom layers. As the name suggests, supported layers are layers directly supported in the OpenVINO toolkit, of which there are plenty, while custom layers are one way to still handle the layers not among the built-in supported layers. Earlier, we saw some of the supported layers when looking at the names when converting from a supported framework to an intermediate representation. While that list is useful for one-offs, you probably don't want to check whether each and every layer in your model is supported. You can also just see when you run the model optimizer what will convert. There's also a further point regarding certain hardware. On CPUs, for instance, there may be certain intermediate representation models that are directly supported, while others are not. We'll see more on this with the inference engine, which can actually directly check for the supported layers for a given device. So what happens when a layer isn't supported by the model optimizer? Are you stuck? One potential solution is the use of custom layers, which we'll go into more shortly. Another solution is actually running the given unsupported layer in its original framework. For example, you could potentially use TensorFlow to load and process the inputs and outputs for a specific layer you built in that framework, if it isn't supported in the model optimizer. Lastly, there are also the unsupported layers for certain hardware that you may run into with the inference engine. In this case, there are sometimes extensions available that can add support. We'll discuss that approach more in the next lesson. Finally, we've arrived at the topic of custom layers. It's one of those important to have features of the OpenVINO toolkit, which you likely won't have to use very often, if at all, due to all the supported layers. However, it's still very useful to know, so let's dive in. The list of supported layers from earlier very directly relates to whether a given layer is a custom layer. Actually, any layer not in that list is automatically classified as a custom layer by the model optimizer. To actually add custom layers, there are a few differences depending on the original model framework. Let's look at the process for Caffe and TensorFlow. In both, the first option is to register the custom layers as extensions to the model optimizer. For Caffe, the second option is to register the layers as custom, then use Caffe to calculate the output shape of the layer. In order to do this, you'll need Caffe on your system. For TensorFlow, its second option is to actually replace the unsupported subgraph with a different subgraph. The final TensorFlow option is to actually offload the computation of a subgraph back to TensorFlow during inference. You'll get a chance to practice this in the next exercise. The exercise is a little bit different than the ones before. There's not going to be a solution video, as the exercise will take you step by step through this pretty complex topic. Because it's such an advanced topic, we won't delve too much deeper here, but feel free to check out the linked documentation if you want to know more. We've covered a lot of topics in this lesson. We went from the basics of the model optimizer, different optimization techniques and their impact on model performance. We covered the supported frameworks, as well as converting models from those frameworks into intermediate representations, and finally, a little bit on custom layers. You've really upskilled on working with the model optimizer. Up next, we'll move on to the inference engine, where you can run these great models even more efficiently at the edge. It's great to have you back. In this lesson, we're going to cover the basics of the inference engine, supported devices, feeding an intermediate representation to the inference engine and making inference requests, handling the results from the inference engine, as well as integrating the inference engine into an application. Since this lesson is all about the inference engine, let's look into what it is and how to use it first. The inference engine runs the actual inference on a model. It only works with the intermediate representations that come from the model optimizer, or the Intel pre-trained models that already are in the IR format. The model optimizer made some improvements to size and complexity of the models to improve memory and computation times. The inference engine, on the other hand, provides hardware-based optimizations to get even further improvements from a model. This really empowers your application to run at the edge and use up as little of device resources as possible. The inference engine has a straightforward API to allow easy integration into your edge application. The inference engine itself is actually built in C++, for CPU at least, leading to overall faster operations. However, it's very common to utilize the built-in Python wrapper to interact with it in Python code. Otherwise, if you've built a C++ app, you can use the C++ API. Now, I've shown the Python wrapper separately in the chart here just to call it out, but it's really a part of the inference engine itself. Now that we've looked at the basics of the inference engine, let's look at the supported devices for it. Now, let's look at the devices supported by the inference engine. The supported devices are going to be all Intel hardware and are a variety of such devices: CPUs, including integrated graphics processors, GPUs, FPGAs, and VPUs. Now, you likely know what CPUs and GPUs are already. FPGAs, or field programmable gate arrays, are able to be further configured by a customer after manufacturing, hence the field programmable part of the name. VPUs, or Vision Processing Unit, is going to be like the Intel Neural Compute Stick. They are small but powerful devices that can be plugged into other hardware for the specific purpose of accelerating computer vision tasks. A later course is going to focus more on hardware, including choosing what hardware to use. Mostly, how the inference engine operates on one device is going to be the same as the other supported devices. However, you may remember me mentioning a CPU extension in the last lesson. That's one difference, that a CPU extension can be added to support additional layers when the inference engine is used on a CPU. We'll look at exactly how to handle that shortly. There are some differences among supported layers by device as well. There's a link in the classroom where you can view these different supported layers yourself, and I'll pull that up just in a second. Another important one to note is regarding when you use the Neural Compute Stick. An easy, fairly low-cost method of testing out an edge application locally, outside of using just your own computer, is to use the Neural Compute Stick with a Raspberry Pi. The model optimizer is not supported directly with this combination, so you may need to create an intermediate representation on another system first. I did add some instructions from Intel on how to use the model optimizer with this combination still. Do note that the inference engine itself, though, is able to work with this combination just fine. Here's the page on supported devices. If I scroll down, I can see the different plugins that are actually available for each of the different devices, as well as some supported configurations. And it's important to notice here the supported model formats. Depending on whether it's CPU, GPU, etc., certain ones of these are not supported. If you're using the Neural Compute Stick, for instance, you'll notice that it's just the FP16 precision that's supported, while CPU and GPU support each of these. There's also the difference here with supported input precision, which will allow you to read on your own. Now, each of these you're not going to have to worry about so much in the exercises in this course. However, this is a useful piece of documentation to be familiar with and use as you dive deeper into the OpenVINO toolkit. Now that you have some of the basics of the inference engine down and know about the supported devices, let's look at how to load an intermediate representation into it. We're going to look at the Python version of the process, following what we've done in earlier lessons. To start, you'll find what you need in the OpenVINO.inference engine library. The two main things we'll want from there are IE core, which is the Python wrapper to work with the inference engine, and IE network, which is what will initially hold the network and get loaded into IE core. Let's go ahead and look at the documentation for each of these. First, Let's start with the IE core documentation. I mainly want to focus on how to initialize this just to start. You notice that this function for initialization actually doesn't look like it takes anything. If you've worked with older versions of the OpenVINO toolkit, you might remember that there used to be what was called IE plugin. IE core replaced that in the newer API. An IE plugin used to need a device name to be filled in here. Now, this only gets used later on, such as when you load the network and you feed the device name. You no longer have to use that when you initialize. Next, looking in IE network, we'll again look at the initialization function. Now down here, we can see that it can take a model and weights. In this case, the model is just the XML file from our IR, and the weights are just the binary file of the IR. So it's pretty easy to initialize each of these. Another key topic is to check for supported layers. Back in the IE core documentation, there is another function called query network. In the documentation, we can see that it takes in the IE network as well as the device name. This device name is just a string, which could be CPU, GPU, or FPGA, as well as myriad, which is used for things like the neural compute stick. This is going to return a list of layers the inference engine supports. You can then iterate through the layers in the IE network you created and check whether they're in that supported layers list. So what happens if a layer wasn't supported? That's where the CPU extension comes in. If layers were successfully built into an intermediate representation with the model optimizer, some of them may still be unsupported by default with the inference engine when run on a CPU. However, there is likely still support for them using one of the available CPU extensions. These do differ by operating system a bit, although they should still be in the overall same location. If you navigate to your OpenVINO install directory, and then deployment tools, inference engine, lib, Intel 64, on Linux, you'll see a few different CPU extension files available for CPU architectures like AVX and SSE. Exactly the difference between those is a bit outside of the scope of the course, but you can look up advanced vector extensions if you want to know more there. On Mac, there's just a single CPU extension file. You can add these directly to the IE core using their full path. Again, I'll leave it to you to check out how to do this in the documentation when you get to the exercise. After you've added the CPU extension, if necessary, you should recheck that all layers are now supported. If they are, it's finally time to load the model into the IE core. Note that you are actually loading the IE network you created previously. Up next, you'll go through all of these steps yourself with a few models in the exercise. And soon after, you'll be making actual inference requests. Nice work! With the IR loaded into the inference engine, we'll soon be able to make inference requests. Let's go ahead and take a quick look at my approach to this exercise. So here we are back in the classroom workspace. And let me go ahead and drag this over so we can view it a little more easily. To start, I made sure to import the necessary libraries. I imported OS mainly just so I can use the name for the XML file towards the binary file for the model. And then from OpenVINO.inference engine, I went ahead and imported the IE network and IE core objects we talked about before. Note that I've added the CPU extension here hard-coded for the workspace, so you don't need to worry about adding that yourself. Below, we can notice from the arguments that we just have to feed in the location of the model XML file and nothing else. Here, let's walk through the to-dos from the exercise. First, to load the inference engine API, I just used the IE core object, and I went ahead and named that plugin. Below, I got the model binary file path just by using the model XML file with the OS library I imported earlier and adding the binary extension at the end. Then, with IE network, we want to load the model, which again is the architecture with the XML, and then the weights with the binary file. Further below, I added the CPU extension. Now for your own, I'll actually suggest that even once you've figured out how to use add extension, you might try running the code without it. You'll notice that some of the models actually don't need the CPU extension that we used here, but at least one of them will. As far as supported layers go, you can use the query network function we discussed earlier. This just takes our network, and then it needs the device name, which in the workspace is just CPU. Now, we can go ahead and iterate through the layers and check for which ones are unsupported layers. This means we can get the layers that are in our network, which will be dictionary keys, and compare them to what was in supported layers. If this list has anything in it for unsupported layers, then we'll need to end the program. Otherwise, the program will crash. So here, I just went ahead and printed out which layers were unsupported so that the user can go and look for any necessary extensions, and noted that they should check for extensions. After that, I go ahead and exit the program with an error. Lastly, to load the network into the inference engine, you can just use the load network function. This just needs our network with the CPU. Since we already know now that there's no unsupported layers, or else we would have exited, this function should execute successfully and give us this message. Let's try this out with one of the models. So here's my command to go ahead and run my solution. It's just Python feed network, and with my model, which I've gone ahead and moved our models into this models directory within the workspace, so it's a little shorter of a path. And we can see we successfully reached the end of the script, which means that the inference engine successfully loaded our IR model. Great. Now that we're able to feed an IR to the inference engine, we'll be able to make inference requests very shortly. Now for the real excitement, sending inference requests to the inference engine. After you load the IE network into the IE core, you get back an executable network. This is what you will send the actual inference requests to. There are two types of inference requests you can make, synchronous and asynchronous. There is an important difference between the two on whether your app sits and waits for the inference or can continue and do other tasks. With an executable network, synchronous requests just use the infer function, while asynchronous requests begin with start async, and then you can wait until the request is complete. These requests are infer request objects, which will hold both the input and the output of the request. We'll look a little deeper into the difference between the two of these in the next video. Let's check out the differences between synchronous and asynchronous requests. Synchronous means to wait and do nothing else for the inference response to be returned. The main thread is blocked in synchronous, meaning that only one frame is going to be processed at once. The next frame is not gathered until the current frame's inference request is complete. On the other hand, you may have heard of asynchronous if you do front-end or networking work. In that case, you want to process things asynchronously, so in case the response for a particular item takes a long time, you're not going to hold up the rest of your website or app from loading or operating appropriately. Async in our case means other tasks may continue while waiting on the inference engine to respond. This is helpful when you still want other things to occur. The app is not completely frozen by the request if the response hangs for a bit. Where the main thread was blocked in synchronous, async does not block the main thread. So you could have a frame sent for inference while still gathering and pre-processing the next frame. You can make use of the wait process to wait for the inference result to be available. You could also use this with multiple webcams so that the app could grab a new frame from one webcam while performing inference for the other. Now that we've gone over the concepts behind making inference requests, both synchronously and asynchronously, you'll implement these in the next exercise. Good luck! Amazing! You now know how to make inference requests to the inference engine. Let's go ahead and walk through my solution for doing so. Back in our workspace, I'll go ahead and drag over our inference file here, and let's take a look. Here, there's a few more arguments to use. We're again going to have our model XML file, but we'll also have the location of the image input, and we'll allow the user to decide whether to use asynchronous or synchronous. This is sort of just for this application to show the differences between the two. Usually, you as the developer would decide on this. Now below, before we get into the exact solution, I just want to show a little bit about this other code. We're once again reading in our image, and we extract the image shape from there. And we're actually going to use our pre-processing function we used long ago in the pre-trained models lesson. Now we can actually iterate through the inputs here, and that's something that we're going to use to feed into our inference request. Now here, since we had an argument that fed in these, that's how I decide in the code to send it to either the async inference or synchronous inference. If it's something other than A or S, we need to end the program because we don't know what the user actually wants. Let's first look at my implementation for synchronous inference. This one is pretty straightforward. With our executable network, we just need to use the infer function, and with our input blob, we feed in the image. This is actually going to directly return the result of the inference, so we can return that here. If we look just at asynchronous inference, we're going to have the same inputs of our executable network, input blob, and image, but it's going to handle things differently. As we mentioned, it starts by starting async. This will have a request ID. Here, I just gave it a request ID of 0 because even though we're implementing async here, we're actually only doing one thing. It's just our image again with our input to the network named as input blob. If you had multiple requests to make, you could be feeding in different request IDs, and then you would refer to these outputs by that ID. Below, I made a while loop. It's going to check on the status and wait if the status isn't equal to 0. If it is, I'm going to wait for a second here. Now, normally we're not going to have to actually wait that long, but if you had a truly complex model, it could actually be taking longer than that. Once the status returned from the wait function is 0, I'll break the while loop, and there is a difference here. I'm not returning the exact result here, which might seem a little weird. I did that before with the synchronous function, but why not with async? Well, the difference is to get the output, we have to go a little deeper than just returning the output from, well, I don't actually see a function here that would return the output. So while down below, I'm going to feed out to our test function with an output from each of these. These outputs are not the same thing. Now, as we move later into the lesson, you'll actually get to handle this output and extract the inference request from synchronous and asynchronous. But we're not going to do that here. You can take a look into the test code if you want to find how that's being done, but we'll soon hit that in the videos. Before we leave, I'll go ahead and run the test just to show that it's actually working. And great, we passed for all 6 tests. In just a few short lines of code, we're now able to make inference requests to the inference engine, both synchronously and asynchronously. Next, let's look at how to actually handle those results. You've loaded your model, you've made an inference request, and it's been done super fast by the inference engine. So how do you get your results? We saw at the end of the previous exercise that the inference requests are stored in a request attribute in the executable network. There, we focused on the fact that the infer request object had a wait function for asynchronous requests. Each infer request also has a few attributes, namely inputs, outputs, and latency. As the name suggests, inputs in our case would be an image frame, outputs contains the results, and latency notes the inference time of the current request, although we won't worry too much about that right now. It may be useful for you to print out exactly what the outputs attribute contains after a request is complete. For now, you can ask it for the data under the output key to get an array of the probabilities or bounding boxes, etc., returned from the inference request. You'll do this as part of an exercise shortly, but first, we should also take a bit of time to talk about the overall integration of the inference engine into an edge application. You've made it through a ton of OpenVINO toolkit fundamentals, and now it's time to integrate everything into an application. Coming up, you'll be converting a model with the model optimizer, loading it with the inference engine, adding any necessary pre-processing steps for the input frame, making inference requests and performing inference, and handling and processing the outputs. And of course, we'll make sure all of this gets built into an application. That sounds like a lot, but you actually know how to do all of this already. I'm throwing in a couple of extra steps that go on top of just the OpenVINO toolkit pieces as well. But we'll go ahead and use some of your inference outputs. The first is to add functionality for different confidence thresholds to determine when to draw bounding boxes for the output. And the other is adding functionality for different colors of the bounding boxes themselves. By the end of the exercise, you'll have fully integrated the inference engine into the app, as well as having some additional customization available for the app's outputs. Good luck, and I'll see you back here soon. Outstanding! You've really worked through the whole workflow here to utilize the OpenVINO toolkit for this app. Since we covered some of the steps before in earlier exercises, I'm going to mainly focus on the new items here, like handling the output, integration into the app, and adding that additional functionality and customization through the command line. You can check out the solution code in the workspace if you are stuck on any of the other parts. Once again, we're back in the classroom workspace. Now, this one was a little bit more intensive of an exercise as you had to go through all the various steps we've learned so far. I'll start out with some of the new things, starting with the inference Python file, and I'll move it over here so we can see it a little easier. So the three parts you had to deal with here were to begin asynchronous inference, wait, as well as extracting the output. Now, you did mostly do the async inference before, but I just wanted to point it out here again. You start async, you'll feed in a request ID because we actually are only feeding in one at a time, although in real asynchronous, you'd want to have that as an input to the function. The inputs here are our input blob, which was actually extracted up here from our network inputs, and then you feed in the image. From there, you need to be able to wait for that request to be complete. And note that I feed a -1 here, so that it will actually wait until that is complete and then return the status code to be 0 that we can now extract our output. This is the first really new part, and you'll see with our executable network, we again feed in our request ID as 0, although again, you may want to add this as an argument parameter if you do actually have multiple requests running. At the end, use our outputs and the self.output blob, which similarly to our input blob from before, we extracted up here by iterating through the outputs. Now, let's go ahead and shift over to the app itself. I'll start with an app that doesn't have all the customizations added in yet, so we'll skip this step for now. Down below, of course, are your earlier steps of initializing the inference engine and loading it. And note here that we have some new code to actually use a video for the first time. You can pre-process the frame similarly to how you've done before. Here, you'll call the async inference function you implemented, and then check whether the wait function returns 0. When you do, you can extract the output. So this is just my function to actually extract the bounding boxes and draw them back onto the original frame. Up above, you can see here, it's just extracting because it's a 1 by 1 to start. I go down a couple dimensions to the 100 by 7, and each of these hundreds is a single bounding box. The confidence is going to be the third item, as the one before that would actually be the class. So if we also wanted to output the class, you could get that from box 1. And then here, I'm just using a default of 0.5 for the confidence. This is now an area I can see that I'll be able to customize here in a second. Now I extract out each of the bounding box points and feed them in to create a rectangle. Here's the color we're going to draw the rectangle in. And remember, because it's BGR for OpenCV, the 255 here is for red, so these bounding boxes will be red. Now let's look at how we would customize this. Now I'm back with a more customized app. Below, we can see how I feed this into our argument parser. So I just added a C description for color and CT description. I think maybe I could also consider BC for bounding box color or something similar as well. And then I add these as arguments. Notice that in my case, I added these as optional and I set a default. So note I'm using a string here, and you'll notice that that is just specific to my implementation. You could potentially feed in a value directly. Here's my confidence threshold, which again, I'll set a default of 0.52. Now I noted with my arg.c for color that I was using a string, and that's because I just map a dictionary back to these values. And remember, it's BGR, so 255, 0, and 0 will be blue, and so on for green and red. Now if I get an invalid dictionary key, meaning someone gave me a color that I wasn't expecting, I'm just going to default to blue, just like I did up in the argument parser itself. Within drawing the boxes, I'm going to make sure I have the args feeding in, and this time, instead of using 0.5 here, I feed in the confidence threshold. Similarly, in drawing the rectangle, I'll feed in the argument color. Down below, you can also see that I extract this here and make sure that I convert the color, which is converting from my string into the values that will actually get fed into CV2 rectangle. And then here, I also make sure that the confidence threshold is a float. You could potentially do that in the argument parser itself. So here, I'll go ahead and run my app from the terminal with my model file, which is actually our TensorFlow model we converted earlier. I'm going to set the bounding box color to green and a confidence threshold of 0.6. So there you have it. You've fully integrated the inference engine as well as all the other parts of the OpenVINO toolkit into an edge application. However, there are some other parts of the edge application that were still implemented for you. There's a lot of different communication and such that still needs to happen for an edge application, and that's what we're going to cover in the next lesson. Before we step into the final lesson, where we'll focus on some more general edge topics, let's take a look under the hood of the inference engine. I noted previously that the inference engine is built and optimized in C++, although that's specific to the CPU version and isn't necessarily the same for all the different devices. These differences under the hood utilize different optimization based on the hardware, although you are able to work with a shared API to interact with the inference engine, while largely being able to ignore these differences. So why is the inference engine built in C++ for CPUs? In fact, many different computer vision and AI frameworks are built with C++ and have additional Python interfaces. OpenCV and TensorFlow, for example, are built primarily in C++, but many users interact with the libraries in Python. C++ is faster and more efficient than Python when well implemented. It also gives the user more direct access to items in memory and such, and they can be passed between modules more efficiently. C++ is compiled and optimized ahead of runtime, whereas Python basically gets read line by line when a script is run. On the flip side, Python can make it easier for prototyping and fast fixes. It's fairly common then to be using a C++ library for the actual computer vision techniques and inferencing, but with the actual application sometimes being in Python, and then interacting with the C++ library via a Python API. As I mentioned a bit ago, the exact optimizations differ by device with the inference engine. While from your end of interacting with the inference engine is mostly the same, there's actually separate plugins within it for working with each device type. CPUs, for instance, rely on the Intel Math Kernel Library for Deep Neural Networks, or MKL-DNN. CPUs also have some extra work to help improve device throughput, especially for CPUs with higher numbers of cores. GPUs, meanwhile, utilize the Compute Library for Deep Neural Networks, or CLDNN, which also uses OpenCL within it. Using OpenCL introduces a small overhead right when the GPU plugin is loaded, but is only a one-time overhead cost. The GPU plugin works best with FP16 models over the FP32 models. Getting to VPU devices, like the Neural Compute Stick, there are additional costs associated with it being a USB device. It's actually recommended to be processing 4 inference requests at any given time. This is in order to hide the cost of data transfer from the main device to the VPU through the USB. Later courses will dive into these hardware differences in more detail. In this lesson, we've covered the basics of the inference engine, the supported devices, feeding an intermediate representation to the inference engine, as well as making inference requests, and then handling the results from the inference engine. You finished up by integrating the inference engine into an application. Next up, we'll take a step back from the OpenVINO toolkit and look into some additional topics useful for edge applications. It's great to have you back. In the final exercise of the last lesson, you integrated everything you've learned so far into an edge application. That app switched us from just images to using videos, as well as creating an output video. However, what about using webcam inputs, or instead streaming information or the output video itself somewhere over the internet? In this lesson, we'll cover some crucial topics to do so, including some more basics of OpenCV, handling input streams in OpenCV, processing model outputs for additional useful information, the basics of MQTT and its use with Internet of Things devices, sending statistics and video streams to a server, performance basics, and then we'll finish up by thinking about additional model use cases as well as some end user needs. Let's get started. To begin this lesson, we'll look into some of the basics of OpenCV, an open source computer vision library. OpenCV is an open source library for various image processing and computer vision techniques. It runs on a highly optimized C++ backend, although it's available for use with Python and Java as well. It's often helpful as part of your overall edge applications. There are a lot of uses of OpenCV. In your use case, you'll largely focus on its ability to capture and read frames from video streams, whether a video file or active camera stream, or an image. It also has other pre-processing techniques like converting from one color space to another, which may help in extracting certain features from a frame. There are also plenty of computer vision techniques included, such as canny edge detection, which helps to extract edges such as the shape of a person from an image. It also extends even to a suite of different machine learning classifiers for tasks like face detection. Here are a few useful OpenCV functions you might want in your edge application. Video capture can read in a video or image and extract a frame from it for processing. As the name suggests, resize is used to resize a given frame, and you've seen this a few times before. Convert color can convert between different color spaces, such as BGR and RGB. You might remember this from back with the TensorFlow models, that they're usually trained with RGB images, while OpenCV is going to load frames as BGR. There was a technique with the model optimizer that would build the TensorFlow model to appropriately handle BGR, but if you didn't add that additional argument at the time, you could use this function to convert each image to RGB, but that will add a little extra processing time. Now you've seen CV2 rectangle a little bit before. This is useful for drawing bounding boxes onto an output image. CV2.imWrite is also useful for saving down a given image. And of course, I suggest taking a look at different OpenCV documentation as well as tutorials if you want to learn a little more. We'll look specifically at handling input streams with OpenCV next. In previous lessons, you got everything set up to perform efficient inference with the OpenVINO toolkit. But what about actually feeding the input into the edge application itself? Being able to efficiently handle video files, image files, or webcam streams is an important part of an edge application. If I were to be running the webcam on my MacBook, for instance, and performing inference, a surprisingly large amount of resources get used up simply to use the webcam. That's why it's useful to utilize the OpenCV functions built for this. They are about as optimized for general use with input streams as you'll find anywhere. We saw the CV2.videoCapture function in the previous video. This function takes either a 0 for webcam use or the path to the input image or video file. That's just the first step though. This capture object must then be opened with capture.open. Then you can basically make a loop by checking if capture.isOpened. And you can read a frame from it with the capture.read function. This function will actually return two items, a Boolean and the frame. If the Boolean is false, there's no further frames to read, such as if the video is over, so you should go ahead and break out of the loop. Once there are no more frames left to capture, there's a couple of extra steps to end the process with OpenCV. First, you'll need to release the capture, which will allow OpenCV to release the captured file or stream. Secondly, you'll likely want to use the cv2.destroyAllWindows function. This will make sure any additional windows, such as those used to view output frames, are closed out. There's actually one other thing to consider while the stream itself is still capturing: checking for key presses. You may want to add a call to cv2.waitKey within the loop and break the loop if your desired key is pressed. For instance, if the key pressed is 27, that's the escape key, such as Control-C on your keyboard. That way you can close the stream midway throughout with a single button. Otherwise, you may get stuck with an open window that's a bit difficult to close on its own. Next up, you'll get to practice some of these skills yourself in the exercise on handling input streams. Great work on this exercise. Now that you've implemented input stream handling and a couple other OpenCV techniques, let's look at my approach. So here within the app, this one's a little different than the last few we've done. I'm only taking in the input file, as we actually won't worry about performing any inference on this video. All you're going to do is take in an image, video, or webcam, although unfortunately the webcam option won't be available within the workspace. Resize it as noted in the instructions, and then you'll also go ahead and perform canny edge detection on each frame and then write it out. Let's go through these step by step. First off, I decided to create a flag for single images. This is mainly because how this is processed is different whether it's an image versus a webcam stream or a video. This is both true when wanting to write to it. Like here, I use the cv2.videowriter to write an output video. As you'll see below, that video writer writes the frame, but if the image flag is true, it's just going to write out a single image file with imwrite. Back up top, you can see that I check the input. In my case, I decided if you used cam as the input, that would set it to 0, which means the input is a webcam. Otherwise, if it's a JPEG or bitmap file, I set the image flag to true. Here, I feed in the input to video capture. And note here, when I open this, I switch the args.i when it's cam, so that instead of actually being cam, it gets switched to 0 by the time you get here. Otherwise, this could also be the video path. So here, if it's not an image, we'll create the video writer. Otherwise, I just set out to none, and we don't need to use it further. From there, I check if the capture is open. I'll go ahead and read a frame, and then I also add in this key pressed with cv2.waitKey so that I can easily cancel out of OpenCV. Further on, as in the instructions, and just to give you a little bit more practice with OpenCV, I had you resize the image to 100 by 100, and then perform canny edge detection. This is with a min value of 100 and a max value of 200. Here, again, as I mentioned, there's a difference with the image flag or without it, where either we use imwrite to write out the output image, or otherwise write to our video writer. Here the key press is checked, and again, this escape character might be Control-C, for instance, on a Mac, where it will break. And then further out, you just need to make sure before you exit the program that you go ahead and release our video writer, the capture, and destroy all windows. Then here in the terminal, this one's pretty straightforward to run. I would just say python app.py and add my input. And for instance, I could use the test video or my blue car, which are the test images in the directory, and see the output. So now we've shown how to handle input streams. This is great to be able to handle lots of different sensor information coming in, especially with cameras. Next up, we'll go ahead and start getting into handling the outputs a little further. You can get a bounding box or some semantic masks, but what do you actually do with them? When training neural networks, a lot of the focus is placed on accuracy, such as detecting the right bounding boxes and having them placed in the right spot. But what should you actually do with those bounding boxes or semantic masks, classes, etc.? What further information can we get from them? Think of semantic segmentation performed over a road scene for a self-driving car. The model says there are people detected. Should the car always stop? If they are in the road or a crosswalk, probably so. But if they are sitting in chairs at a cafe off to the side, that's probably not incredibly important, as long as your car keeps to its lane on the road. How about if you have a pet with a particular affinity for eating trash? You could ban him from the room where the trash can is, but he might still ignore the rules when you aren't home. If you detected your pet near the trash can with your webcam, perhaps you could play a sound to remind him to stay away. It's really important to get useful information from your model. Information from one model could even be further used in an additional model. Traffic data from one set of days could be used to predict traffic on another set of days, for example, such as near to a sporting event. Let's consider some basic logic to extract useful data from the model outputs. In the road scene, you could perform an analysis on what the pedestrian class appears over. Is it a road or a sidewalk? Or in this case, it could even be combined with other sensor data. Is the pedestrian moving toward the road or away from it? For the pet getting in the trash, if the bounding box for the trash can and the dog overlap at all, play the warning sound. For the traffic example, you likely want to count how many bounding boxes there are, but making sure to only count once for each vehicle until it leaves the screen. You could also consider which part of the screen they come from and which part they exit from. Does the left turn arrow need to last longer near to a big event? Maybe this might happen if all the cars seem to be heading in that direction. In an earlier exercise, you played around a bit with the confidence threshold of bounding box detections. That's another useful way to extract statistics. Are you making sure to throw out low confidence predictions? In the next exercise, you'll put some of this into action to keep some unfriendly pets apart. I hope you had some fun with this exercise. It seems like it's maybe something that could happen in real life and something you might want to implement at home. Let's go ahead and walk through what I did in this exercise. Just to go back over the background of this exercise, we have 3 pets at home, a cat and 2 dogs. The cat and one of the dogs get together fine, but the cat and the second dog always get into fights when they're around each other. So, for this IoT device, we're going to use a webcam essentially. In our case, it'll be an input video, but check whether what we see is the cat and dog number 1 together or the cat and dog number 2. It could also be, of course, that none of the pets are on there or only one of the pets or both dogs. Really what we're mainly concerned about is the cat and dog number 1 and the cat and dog number 2. Now the model that's used for this is super basic. It's really only going to put out 3 classes. Really what this is as if you had an object detection model first that could tell you the dog breeds and maybe that there's a cat in the image, and then you processed it a little further just to put them into the 3 categories of having no pets or the 2 dogs on screen or just 1 pet. Another class that's when it's a cat and dog number 1, and another class that's the cat and dog number 2. Let's check out what the input video for this was so we can see exactly what we might expect. Here's the friendly dog and the cat, and it's interspersed with the dog and the cat that are confrontational. As we go through the video, in fact, we can see they're fine, but near the end, the dog and the cat that don't like each other are going to get in a fight. So let's look at our application. First, we're mainly just going to have to input the XML file for the model, as well as the input file, although I went ahead and fed it in directly from our exercise. And then down below, let's look at what I did when it infers on video. Most of this code is what we've covered in the previous exercises, so you actually didn't have to do too much with the rest of it. The main thing I did here is in my assessing the scene function. You might wonder what exactly this incident flag is that I added, and it's actually so I can track whether there's a current ongoing incident. What I decided to do was send in the result and a counter as well as the incident flag. And note that my counter here starts at 0, and I'm basically trying to use it for the timestamp, essentially. I look at this and say, using my result, because the second class, or 1, for 0, 1, and 2, is the one that's the bad combination. If there's not a currently ongoing incident, I want to go ahead and get my timestamp, which I got from my counter, and here's 30 for 30 frames per second. And I want to log when the incident happened, and then tell my pets to break it up. In this case, I go ahead and set the incident flag to true. This means that the next time around, I'm not constantly starting up this message because if I just sit there and keep hitting the same sound again and again and again at each of 30 frames per second, well, the pets probably won't ever get the idea. In the other cases, when either there aren't pets on screen or it's the friendly dog with the cat, the incident flag gets set to false, so it can reset. Let's look at the app in action. Here I'll run my app, and my model XML file is already here in the directory with me. So note it's going to take a few seconds to run, but each time there's an incident in the video, we'll get out a timestamp and get to see break it up. So the first one happened at 3.8 seconds, and if you time that against the original video, that's about when the unfriendly dog and the cat appear. A second incident happens at 10.87 seconds, and again, they get a break it up message. Note that this is just when the video is playing. One thing I didn't implement in the app was to actually check for if the incident has gone on for a long time. Maybe I would want to replay my message, say once every 10 seconds or something. In this case, it was just because of how the video was cut up that it tended to work out that way. And that's it. We saw here that I went ahead and delayed these messages a little bit. This is good so that we're not constantly sending information that's just repeating the same thing again and again. You probably wouldn't constantly want to get alerts at work that your pets are having difficulties with each other. However, in this fashion, you process the data a little bit and you make sure you cut down on the amount of data getting sent. In this case, we saw that we want to keep this a little bit more lightweight, and already understanding this will help us a lot going forward. Coming up, we'll look at MQTT and FFmpeg, which will help with sending statistics and image frames over the internet. Now that you've looked at how you can process information and make sure you're not sending too much of it, both of these methods will be really useful for building your edge applications. Now, you're able to take an input stream, perform inference on it, and extract some additional useful information from the output. What if you want this information to be available somewhere else? Going forward from the pet example, maybe you want to open a web page or an app on your phone where you can receive the data, both on how many times the cat and the dog got caught in the same room, as well as even a recording of when that happened. We'll first look at MQTT, which is useful for sending small portions of data to servers, as well as a technique for sending frames of video to a server. MQTT stands for MQ Telemetry Transport, where the MQ came from an old IBM product line called IBM MQ for message queues, although MQTT itself does not actually use queues. Now, this doesn't really give a lot away about its usage. Really, it's useful because it's a lightweight publish-subscribe architecture, and it's designed for resource-constrained devices and low bandwidth setups. This is used a lot for Internet of Things devices or other machine-to-machine communication, and it's been around since 1999. Port 1883 is reserved for use with MQTT, and you'll see us use that with servers later. On the last slide, I mentioned the concept of publish-subscribe. In this architecture, there is a broker or hub that receives messages published to it by different clients. It then routes the messages to any client subscribing to those particular messages. This is managed through the use of what are called topics. One client publishes to a topic, while another client subscribes to that topic. The broker is going to handle passing the message from the publishing client on that topic to any subscribers. These clients don't actually need to know anything about each other, just the topic that they want to publish or subscribe to. MQTT is just one example of this and is very lightweight. While you could publish information, such as the count of bounding boxes over MQTT, you cannot publish a video frame using it. Publish-subscribe is also used with self-driving cars, such as with the Robot Operating System, or ROS for short, where a stoplight classifier may publish on one topic with an intermediate system that determines when to brake subscribing to that topic, and then that system may publish to another topic that the actual brake system itself subscribes to. Moving on from the basics of MQTT and publish-subscribe, I want to show you how to work with MQTT in Python. There is a useful Python library for working with MQTT called PayHo MQTT. Within, there is a sub-library called client, which, as you may guess, is how you create the MQTT client that can publish or subscribe to the broker. Now, you'll need to know the IP address of the broker, as well as setting the port for it. With those, you can then connect to the client, and from there, you can either publish or subscribe to different topics. Publishing involves feeding in the topic name, as well as a dictionary containing a message that is dumped to JSON. Subscribing just involves feeding in the topic name to be subscribed to. At the bottom of the page, I've linked the documentation for this library. You can use it to answer the quiz below on the proper syntax for publishing and subscribing in Python. You'll also get to use it in a later exercise, for after we've covered streaming videos to servers as well. Before we move on, it's important to remember your Python MQTT client is actually sending its message to a broker server first. So, if you wanted to view data from your Python app on a web page somewhere, that web page would actually include code to subscribe to the server, not your Python client. Later in this lesson, we'll show you how a node server can be used to accomplish this. In fact, in the project, you'll end up with two node servers. One that acts as the MQTT server, and one that subscribes to that server and actually publishes a web page. Most of the specifics of that are outside the scope of the course, so these servers will be given to you to interact with from your Python application. Next, let's look at streaming video to a server, the other thing that final node server will be able to receive. Sometimes you may still want a video feed to be streamed to a server. Think about if you had a security camera that could detect a person where they shouldn't be and then send an alert. That's pretty useful on its own, but then you'd probably still want to view the footage itself. At the start of the course, we noted that network communications can be expensive in cost, bandwidth, and power consumption. Video streaming consumes a ton of network resources, as it requires a lot of data to be sent over the network, clogging everything up. Even with high-speed internet, multiple users streaming video can cause things to slow down. As such, it's important to first consider whether you even need to stream video to a server, or at least only stream it in certain situations, such as when your Edge AI algorithm has detected a particular event. Of course, there are certainly situations where streaming video is necessary. The FFmpeg library is named as fast-forward MPEG, meaning it's supposed to be a fast way of handling the MPEG video standard, among others. In our case, we'll use the FF server feature of FFmpeg, which, similar to MQTT, will actually have an intermediate FFmpeg server that the video frames are sent to. The final node server that displays a web page will actually get the video from that FFmpeg server. There are other ways to handle streaming video as well. In Python, you can also use a Flask server to do some similar things, although here in this course, we'll focus on FFmpeg. You can download FFmpeg from ffmpeg.org. Using FF server requires a configuration file that we will provide for you. This configuration file sets the port and IP address of the server, as well as some settings like the ports to receive video from and the frame rate of the video. These settings can also allow it to listen to the system standard out buffer, which is how you can send video frames to it in Python. With the sys Python library, you can use sys.standardout.buffer.write with an input frame, as well as flush it to send the frame to the FF server. If you have an FFmpeg folder containing the configuration file for the server, you could then launch the FF server with sudo ffserver-f with a configuration file. You can do this from the command line. To actually capture these output frames with FFmpeg, they need to be piped into FFmpeg when the Python script is run. This is done with the pipe symbol, followed by FFmpeg and then any related arguments. Some of these could be format, pixel format, video size, and frame rate, etc., just like we saw with the configuration file. So, what actually receives the output from the FFmpeg server? That could be a final node server with the UI, or just another server for storage. Let's go ahead and look at what node is next. So far, I've mentioned node servers a few times, so let's briefly cover what exactly these are. Node.js is an open source environment for servers, where JavaScript can be run outside of a browser. Think about a social media page, for instance. That page is going to contain different content for each different user based on their social network. Node allows for JavaScript to run outside of the browser to gather the various relevant posts for each given user, and then send those posts to the browser. In our case, a node server can be used to handle the data coming in from the MQTT and FFmpeg servers, and then actually render that content for a web page user interface. In the upcoming exercise, as well as in the project, you'll be given the main node servers, one for the UI and one for the MQTT server. It will be your job to communicate with them from the Python app. Note that you can also utilize a more basic front-end with HTML and CSS for a web page like this. But these type of front-end skills are outside the scope of this course. Using these type of servers, though, is closer to a more end-to-end piece for the Internet of Things. So you've built out your app, but what happens to the information you processed at the edge? Someone or something probably wants to receive that data. Outstanding work. You can now use all the pieces necessary to build an edge application, as well as send its data to a server. Let's go ahead and take a quick look at my approach. Back in the classroom workspace, we'll first look at how I used MQTT, as well as sending the output frame with FF server. Let's go ahead and look first at what the input and output videos were for this, just in case something on your side wasn't going to the browser correctly. Our input video is just a very short video of a car driving down a highway. However, this could be used in a self-driving car application. The output video of our network is the semantic mask of the car driving along. A self-driving car might seem like an odd application of sending data over the internet, but think about if a car had an accident. You might want to know data about the steering angle, the speed, acceleration, as well as what it saw around it as the accident occurred and before it. So here we are in the app, and I've made sure that I import MQTT here, and I've used an alias to shorten it a little bit. I've also gone ahead and used socket, which I'll use to actually load the host name and IP address for MQTT. Note that I've set the port here, although you will need to actually check and make sure the MQTT server is configured on this. This is the standard, but it could be different in different situations. Above, we'll see that there are different classes that the output uses. And then right when I start to actually infer on video, before I even load the inference engine in, I'm going to go ahead and establish my MQTT client and use some of the data above. Note that this keep alive interval just make sure to check every once in a while that the connection hasn't been canceled from the other side. Down below, I'm going to go ahead and publish some of the class information and some data from the speedometer. I actually just created this for you, just a random speed, but again, it's just another example so you can practice using topics with MQTT. Below that, and outside of the inference request, I've actually gone ahead and used system.standardout to write out the output frame and flush it. At the very bottom, when everything's done running, in our case the video is done, I go ahead and disconnect from our MQTT client. Now, at this point, just because you entered in these two lines for FFmpeg doesn't actually send that to the FFmpeg server. You still need to make sure to feed it in when you run the app itself from the command line. Let's look at how to run this app within the workspace. I have a few different terminal windows open. Note that if you need to open new terminal windows, you can use New, Terminal up here in the menu from File, and you'll be able to open more terminals. In this case, this application actually needs 4 terminals open. Here we have one for the node server related to the MQTT broker server. This one will handle the UI. We have another one that will handle FFmpeg, and the last one will actually run the Python app. So to start, we'll do node./server.js, and we should see that our Moscow server, which in this case is our MQTT server, has started. Over here, within the UI folder, if we use npm run dev, this will go ahead and compile Webpack, and it'll take a few seconds here, but at the end, it should tell us that Webpack has compiled successfully. And here, we now know that the UI is ready to go. Next up is ffmpeg, in this case, the FF server, and we're just feeding in our configuration file. Here, we can see that the FF server has started. Now we can actually run the app. So again, we'll start with actually running the app, but we need to feed in ffmpeg with the pipe symbol. This means that the information coming from our Python script will get fed to ffmpeg, or piped to it. Here, I'm also just saying that I want to see any warnings that might come out of it. It's going to be in the format of raw video. The pixel format is BGR. This is our video size, frame rate, and then this is actually part of our configuration file. And the IP address here is from the configuration file as well as the port. And this is just the file that the FF server is actually going to pick up from. Now, if I run this, we won't actually see much output over here, but because we had the MQTT server over here, we'll be able to see what's getting published. We'll see that both our classes and speedometer is getting published. Here in the workspace, you can click on Open App, and it'll take a second to actually load our image here, but we'll be able to see that we have our classes counted and speed coming in, as well as the image that's our semantic mask output. Note that this will run a little bit slow, and that's just because semantic segmentation is pretty resource intensive. In this application of a self-driving car, you'd probably have a GPU in the car so that you had additional acceleration. We won't see more on GPUs until later courses, but this is one potential application where you can see that you might want to try out different hardware devices. You've come a long way with your edge skills. Now, we'll take a step away from all the code and try to use additional thinking and analytical skills to further build up on your applications. We're now through the programming parts of this lesson, and to finish things off, I want to cover some more decision-based and analytical topics. We've talked a lot about optimizing for inference and running apps at the edge, but it's always important to not skip past the accuracy of your edge AI model. Lighter, quicker models are helpful for the edge, and certain optimizations like lower precision that help with these will have some impact on accuracy. No amount of skillful post-processing and attempting to extract useful data from the output will make up for a poor model choice, or one where too many sacrifices were made for speed. Of course, it all depends on the exact application as to how much loss of accuracy is acceptable. Detecting a pet getting into the trash likely can handle less accuracy than a self-driving car. Now, the considerations of speed, size, and network impacts are still very important for AI at the edge. Faster models can free up computation for other tasks. They can lead to less power usage and allow for the use of cheaper hardware. Smaller models can also free up memory for other tasks or allow for devices with less memory to begin with. We've also discussed some of the network impacts earlier on. Especially for remote edge devices, the power costs of heavy network communication may significantly hamper their use. And lastly, there can be other differences in cloud versus edge costs other than just network effects. While potentially being lower up front, cloud storage and computation costs can add up over time. As we discussed earlier on, data sent to the cloud could be intercepted along the way, although this does depend on a secure edge device, which is not always the case for the Internet of Things. Throughout the course, we've hit a lot on different use cases for edge applications. It's important to think on any additional use cases for a given model or application you build. These can go far beyond the original training set or intended use. For example, object detection can be used for so many different things. If a given model is mainly focused on particular classes, along with some post-processing, there can be very different applications that come from it. As another example, think of pose detection. It's useful for video games such as dancing, motion capture, and tracking movement. Exercise applications And even health applications, noting posture or even that something could be wrong, are additional use cases that could be used here. Before we close out this lesson and the course, I want to add a final note on considering the needs of your application's end users. If you are building an app for certain end users, it's very important to consider their needs. Knowing their needs can inform the various trade-offs you make regarding model decisions, such as speed, size, and accuracy, as well as what information you send to servers, security of information, etc. If they have more resources available, you might go for a higher accuracy, but more resource-intensive apps, while an end user with remote, low-power devices will likely have to sacrifice some accuracy for a lighter, faster application. They'll also need some additional considerations about network usage. This is just to get you thinking. Building edge applications is about more than just models and code. In this lesson, we added some more edge skills to your repertoire by covering basics of OpenCV, handling input streams in OpenCV, processing model outputs for additional useful information, the basics of MQTT and their use with Internet of Things devices, sending statistics and video streams to a server, performance basics, and also covered thinking about additional model use cases as well as end user needs. In this course, you've gone from the basics of AI at the edge to building your skills with pre-trained models, the model optimizer, the inference engine, and more with the Intel distribution of OpenVINO toolkit, as well as learning extra topics about running an app at the edge. You've already accomplished a great deal, and I'm so excited to see what else happens at the edge with you on the forefront.